Hello learners, welcome to this course on Embedded System Design using PIC16FA77 microcontroller. In this tutorial, I will be discussing about on how to use, configure and program your UART in PIC16FA77 microcontroller. So UART stands for Universal Asynchronous Receiver Transmitter. So universal asynchronous receiver transmitter, in the sense we are going to transmit the data to any external device. It can be a computer or it can be any peripheral device. So the data transmission is going to happen in a serial fashion. So serial fashion, in the sense bit by bit transmission is going to happen. So the data is going to be transmitted using a hardware UART inside your microcontroller. So here this UART is an asynchronous serial transmission, which means the data is transmitted asynchronously without the help of a clock signal. So the clock signal is not used for your data transmission and reception. So the data can come at any time and it can be transmitted at any time. So here the important thing is we can configure the data format, like we have a 8-bit format as well as a 9-bit format, and also the transmission speeds can be varied. So transmission speed, in the sense the speed of the data transmission is measured using baud rate. So baud rate is nothing but number of bits transmitted per second. So the transmission speed can be configured, it can be varied. And another important thing with your UART is the signaling levels in your microcontroller for a UART will be different, whereas for the external device like a computer it will be different. So we should have a driver circuit which converts the electrical signal format of a microcontroller to that of electrical signal format of an external device, same way vice versa. So those conversion, electrical signal conversion should be added. So those things can be done with the help of a driver circuit. And the application for this UART is we can use it for communication to other computer or peripheral devices like mouse, printer, monitors, etc. If I take two devices with UART capability, we essentially use three lines for your data transmission and reception. So there is a transmitter line which is indicated by TX, there is a receiver line which is indicated by RX, and the signals in this TX and RX will vary with respect to the ground line. So in order for data transmission to occur between two devices, so here you can see one device transmitter is connected to the receiver of another device. Same way another device transmitter is connected to the receiver of the first device. So the transmission needs to be connected to receive pin, and the receiver from one device it needs to connect to transmitter line. And the signaling of this transmitter and receiver line will vary with respect to the ground line. So that is how a data can be transferred from one device to another device using this UART communication. So if we see the packet format for this UART communication, it has a start bit. So the start bit is indicated by a high to low pulse. A high to low pulse. So if it is a microcontroller, then the high will be considered as 5 volt and low will be considered as 0 volt. So there will be a transition from 5 volt to 0 volt. So it indicates the start bit. Then I have a 7-bit data or 8-bit data, depending upon what type of data format we are going to use. So 7-bit data or 8-bit data, and then we have an optional parity bit. So the parity bit is an optional one, whether we can use it or not. So here I can specify whether the data is a even parity or odd parity. So the parity indicates how many ones are there in the data. So if I have odd number of ones, then it is called as an odd parity. If I have even number of ones, then it is termed as an even parity. Then finally we have a stop bit. So stop bit is a low to high transition. So this is the packet format of a UART communication to send one character. If I want to send multiple characters, then many such packets needs to be generated by the UART module. Let us discuss this packet format with the help of an example. So let us assume that I am going to transmit M, capital M, to another device. Then the ASCII value American Standard Code for Information Interchange, which is a universally accepted binary bit pattern for each and every characters, numbers as well as symbols. So if I take the ASCII value of M, it is to be 1001101. So if I count the number of ones here, it is odd number of ones. I have 4 ones, so it is an even parity signal. So how this data, how this M will be transmitted in the sense, first initially there is a high to low transmission which indicates the start bit. Then the next bit after the start bit will be your LSB bit. Okay. So LSB bit will be transmitted. So LSB bit is 1. Then the subsequent bit is 0. Then the next bit will be 1, 1, 0, 0, 1. So finally your MSB bit comes. So while data transmission of UART serially, first the LSB bit will be transmitted and finally the MSB bit will be transmitted. So after the data, depending upon whether it is an odd parity or even parity, in this example, we have taken it as an even parity. So even parity is indicated by 0. If it is an odd parity, it will be indicated by a 1. So the parity bit can be included. It is an optional one. It is up to the programmer to decide whether we need to use a parity bit or not. Then after the parity bit, we have a stop bit. So stop bit will be from 0 to 5 volt in case of a microcontroller. So this is the UART signaling format in a microcontroller. But the data, when it goes to some external device like a computer, there the electrical signals will be of different voltage level and different format. So if I see a computer, in that case, a start bit is usually a high to low. The format is same, but the voltage levels is going to vary. In case of a computer, the logic 1 is represented by minus 12 volt. Logic 1 is represented by minus 12 volt and logic 0 is represented by plus 12 volt. In case of a microcontroller, logic 0 is represented by 0 volt, logic 1 is represented by 5 volt. So for a computer, it is quite different. So logic 0 is represented by plus 12 volt, logic 1 is represented by minus 12 volt. So as we see, the first initially we have to have a 1 to 0 transmission. So 1 here is minus 12 volt. From minus 12 volt, there is a transition to plus 12 volt. So this indicates the start bit. Then comes the data lines. If the LSB data is 0, in that case, we will have a voltage level of plus 12 volt. Then if the bit is 1, we will have a voltage level of minus 12 volt. So the LSB to MSB is being taken care. Then depending upon the data, for example, if I want to send J, so J is this one. So first we will transmit 0, 1, 0, 1, 0, 0, 1, 0. So finally the 0 will come. After the 0, we try to put the optional parity bit. So here I have an odd number of ones. So the parity bit will be 1. So after parity bit, the stop bit will go from logic 0 to 1 transmission, which is from my plus 12 volt to minus 12 volt. So that is how the data will be accessed by your computer. So now we have two different types of format. So one is in your microcontroller, another one is in your computer. So we should have an interfacing circuit which converts this type of a voltage level to this type of a voltage level. So we need to have something like a level shifter in between. So for that we make use of a IC termed as MAX 232. So MAX 232 is a very popular IC which is used as a voltage shifter. So voltage shifter, as well as it can also be called as a voltage doubler, because the voltage initially the microcontroller it is from 0 to 5 volt. Now it has to be changed to plus or minus 12 volt or plus or minus 9 volt. So if I try to see the pin details of this MAX 232, it is a 16 pin IC. So where it has certain capacitors like C1, C2, C2 plus, C2 minus. So these capacitors will be used in producing the appropriate voltage, and we can connect the data from a microcontroller to these pins, and the data out from this IC can be given to your computer. So if I see the circuit diagram, you can see here the C1 is connected to a electrolytic capacitor. So we can use a value of about 1 microfarad or 10 microfarads. So we connect the electrolytic capacitor of 10 microfarad between C1 plus and C1 minus. Same way C2 plus and C2 minus also we connect a capacitor. Then V plus is connected to a capacitor and then to a supply. V minus is also connected with a capacitor and then to a ground. So the lines from your microcontroller will come to T1 in and R1 out, and the output from your MAX232 will be T1 out and R1 in. So this data can be connected to the DB9 connector. So this DB9 connector can be connected to the PC. So DB9 stands for, it's a 9-pin connector. So the second line is your receiver line, third line is your transmitter line. So you can see the T1 out is connected to the receiver part and R1 in is connected to the transmitter part. So here I show a typical DB9 connector which is available in two formats, a male connector as well as a female connector. So here I show a female connector, here I show a male connector. So if we see the pin details here, for a male connector, the pin number 1 is on the left side. For a female connector, the pin number 1 is on the right side. And it has different pins. The important 3 lines are RxD, TxD and ground line. So these 3 lines are used in your UART communication. So other lines like DTR, CD, DSR, RTS, CTS and RI, these are handshake signals. So if we require, we can use it or we can avoid it. So if I see these handshake lines, which are nothing but DTR is data transmit, CD is a carrier deduction, RI is a ringing indicator, CTS is clear to send, RTS is request to send, and DSR is data set ready. So these lines are handshake lines, whereas the data transmission happens mainly due to this TXD and RxD line. These voltages will vary with respect to the ground line. So this is the pin details for your DB9 connector, and this DB9 connector can be connected to your computer, and the data transfer can happen between your microcontroller to the PC, from PC to the microcontroller. So now in this program, what we are going to do is we are going to use a PIC16FA77 microcontroller which has an inbuilt UART. So the UART lines are connected to RC6 and RC7. So RC6 is your transmitter line, RC7 is your receive line. So these two lines are connected to the MAX232 driver. So to T1 in and R1 out. The output from the MAX232 driver is T1 out and R1 in, and it goes to transmitter and receiver pin of your DB9 connector. And this DB9 connector can be connected to your computer for transmission and reception purpose of the data. So now let us go and look at the program, how to send the data from a microcontroller to a PC, from PC to a microcontroller, and also we would like to see how the hardware looks like. So for this application, we will be using MicroC Pro for PIC as an integrated development environment, where we'll be writing the embedded C program, and then Proteus 8 Professional for building the circuit and for testing our MicroC program. So first let us start with the Proteus part. So here I have created the circuit. So here we have used a PIC16FA77 microcontroller, and it is connected with a crystal of 20 MHz crystal. And in order to produce a stable frequency, we have connected a 33 picofarad capacitor. So this crystal is connected to the oscillator 1 and oscillator 2 pins of your microcontroller. So this is your oscillator circuit. Similarly, we have connected the memory clear pin to the reset circuit here. So by default, this pin will be at logic high. So whenever I close the switch, what happens? This pin will go to logic 0, then reset operation will be carried out. So this is your reset circuit. Then as I said, RC6 is your transmitter line, RC7 is your receiver line for your UART. So these two lines are connected to your MAX232 T1 in and R1 out, and the shifted output, it comes from your R1 out and R1 in, and this data goes to your terminal window. So this terminal window I have used instead of a DB9 connector to visualize the output. So this is how we create a circuit for your UART. Now let us go and discuss the program part in micro C. So this is the UART program. So here we have selected the microcontroller. We have set the oscillator frequency to be 20 megahertz. So now let us discuss about this program. So I try to initialize a variable UART. Then in the main program, first thing which we do is we configure the port C. Since RC7 is a receiver line, we set that value to be 1. Receiver line means it's an input. So input means the data direction bit will be 1. For output, it will be 0. So since RC6 is your transmitter line, it is configured as an output line. So RC7 is configured as an input, RC6 is configured as an output. Then we specify the data rate, at what speed the data should be transmitted. An important thing here is both the transmission device and the receiver device should be synchronized with respect to the baud rate. If I use a 9600 baud rate at the transmitter side, then the receiver also should receive the data at the same rate. If there is a mismatch, then the proper reception of data might be affected. So here we use a baud rate of 9600 bits per second. So we have to give some time for the UART to get initialized. Then we are going to send the data from your microcontroller. So from the microcontroller, I am going to use this command UART1 underscore write text to send the data start to the external PC or external device. Then after sending the data, we send a line feed, new line character and a carriage return. Then in a while loop, I am going to check whether any data we are receiving from the receiver device. So in order to check that, I use a library function which is called as UART1 data ready, whether any data is received by the microcontroller. If the data is received, then we read the data, put it onto the variable. Then I am going to send this data, whatever data I have received, I am going to send it again to the computer or any peripheral device. So whatever data we receive, the data again we are going to transmit it to the device. So we pick the data using UART1 underscore read, and the same data is sent back using the write function. Again a line feed and a carriage return is used. Then I am going to check if my data received is 1. Okay, 0x31 is nothing but the ASCII value for your 1. So if I see the ASCII chart, so for 1 you can see it is the ASCII value is 0x31. So if the external device has sent to 1 to the microcontroller, I am going to check whether it is 1. If it is 1, I am going to send it as received 1. If it is some other character other than 1, then in that case I am going to send it is received none. So what we are essentially doing is, first from the microcontroller we are sending the start, then we are waiting for the response from the other device. If the other device sends 1, we send back received 1. If the data sent by the other device is some other than 1, then we send received none. So this completes the UART program. So once programming is done, we build the circuit to convert this C program into a hexadecimal file. Then we go to the Proteus environment. Here we try to dump that hexadecimal file onto the microcontroller. So right click the IC, edit properties, select the program file. So program file is your UART. It's a X file we are trying to dump onto your microcontroller. Then select the processor clock frequency. So processor clock frequency is 20 megahertz. Okay. So now we have dumped the program onto your microcontroller. So before checking the program, I want to check the property of this hyperterminal. So right click on this hyperterminal, edit properties. So here you can see it is synchronized with 9600 baud rate. So that is the same baud rate which we have used in our program. And I'm going to use 8 data bits, 1 stop bit. And if you see the transmitter and receiver polarity, we have set it to inverted. Because in microcontroller, the signals are different. In a PC, the signals are different. So it is an inverted fashion. So logic 0 in microcontroller is 0 volt. Logic 1 in a microcontroller is a 5 volt. Whereas in case of a PC, what happens? Logic 0 is represented by plus 12 volt. Logic 1 is represented by minus 12 volt. So it is an inverted fashion. So we set the transmission and reception polarity to be inverted. Once this configuration is done, we can check the output when I press the play button. You can visualize a start signal has been sent by the microcontroller. So now the data has been received by the external device. Now the microcontroller is waiting for the response from the external device. So for example, let us assume the external device is going to send 1. So I am going to press the switch 1. When I press 1, the microcontroller has said it is received 1. Now again it is waiting for some other response from the external device. If I press some other character, I am going to press right now 5. So when I press 5, you can see it is saying received none. So if 1 is pressed, it says received 1. If some other character is pressed, it says received none. So that is how a UART transmission can be done with the external device. So like this, what we can do is we can connect, instead of a computer, I can connect a GSM module, I can connect a GPS module, any device which supports UART communication that can be connected. And the microcontroller can send the data to the device, it can receive data from the device. So with the help of that, lot of interesting applications can be developed. So in this tutorial, I have discussed about on how to use a UART in PIC16F877 microcontroller, how to configure it, how to program the UART. Thanks for watching. Please subscribe for more technical learning. Thank you.